All right, we are looking at an example here of how we can calculate the discrete time Fourier transform for a periodic signal. So we're going to find the Fourier transform of xn equals cosine of 2 pi over 5 times n, plot the result. Now, the first thing you need to ask yourself is the signal periodic? And in this video, it seems a little goofy to be asking that because we're dealing with periodic signals according to the video. But in reality, or in the class, or whatever, you may or may not know offhand if it's periodic or not. So that's the first question that you have to answer. Is it periodic? If the answer is no, then you use the analysis equation. If the answer is yes, then you go right to form fitting. So and by that I mean the Fourier transform fits this form: 2 pi times k equals minus infinity to infinity of ak delta of omega minus k omega 0. So that's the Fourier transform, but to completely specify the Fourier transform, you have to find the AKs, so you have to find the Fourier series coefficients. So let's do that. Cosine is related to complex exponentials, so we can find the Fourier series coefficients very quickly by using Euler's formula. So we can break the cosine into complex exponentials, and we write xn as 1/2 e to the j 2 pi over 5n plus 1/2 e to the minus j 2 pi over 5n, like this. And I guess we should have asked ourselves also, what's the period and the frequency of 2 pi over 5 after determining it is periodic. Well, you should know, or quickly, maybe, hopefully, that the period is n equals 5 and the frequency is 2 pi over 5. And so we look at this now and we say, okay, well, what constant is multiplying 2 pi over 5? And that is 1. So this is the first harmonic. And here, what constant is multiplying 2 pi over 5? Minus 1. So this is the minus first harmonic. This makes a1, the coefficient in front of the sinusoid, 1/2. And this makes a minus 1, the coefficient in front of the sinusoid, also equal to 1/2. Now, what you have to remember is that in discrete time, the Fourier series coefficients are also periodic with the same period. So that would make, a6 equal to 1/2, a11 equal to 1/2. We can go the other way, right? We can go the other way, say a minus 4 equals 1/2, because when I add 5 to it, that's a1. And if I go backwards, a minus 9 equals 1/2, and I can keep going. Okay, so those are all non-zero. And also then, if a minus 1 is 1/2, then a4 is 1/2, a9 is 1/2, and I can go that way, keep going that way, or I can go backwards. A minus 6 is 1/2, a minus 11 is 1/2, and so on. So these are all of the non-zero Fourier series coefficients of this signal, and we deduced all of that just from 2 pi over 5, right? Okay, so we're gonna move on now that we've got the Fourier series coefficients. So with the Fourier series coefficients specified, and with this formula, we've actually answered the first part of this question. Find the Fourier transform of x. Well, here it is. It's right here. And we've got the AKs. There it is. All right. So now the rest is to plot the results. So we're gonna go ahead and plot that. And so I've got my omega axis. There's omega. I'll draw the origin. All right. Now, do I have any frequencies? Do I have any DC frequency? No. I have no constant in x of n, so I don't have anything at the origin. The frequency I do have is 2 pi over 5, so maybe this is 2 pi over 5. 2 pi over 5, and it is scaled according to 2 pi, right? 2 pi times the AK. So let me back up, actually. So this is what we're plotting in the box, circled anyway. 2 pi times this sum. So this sum has these AKs, but most of them are 0 except for all of these that we've listed. So for example, the k equals 1 term is 2 pi times A1 times delta of omega minus omega 0, and omega 0 is 2 pi over 5. So this is the k equals 1 term. So what is this? This is an impulse that has been shifted to the right by 2 pi over 5, scaled by 2 pi times A1. A1 is 1/2, so this is pi, scaled by pi. So we have this impulse. That's the k equals 1 term. So then we keep going, right? We have to keep going. So the k equals 2 term, A2 is not listed here. A2 is 0. A3 is 0. A4 is 1/2. So we're going to try the k equals 4 term. So this is 2 pi times A4, right? We're going to add this to our sum, A4, delta of omega minus 4 times 2 pi over 5. So this is 8 pi over 5. So we're going to plot that. So maybe this is 8 pi over 5. Scaled by 2 pi times A4, so that is pi. So notice the A1 term came from this sinusoid, and the A2 term, the A1 term came from this sinusoid over here, and the A4 came from this sinusoid over here. So actually, you know what? I'm gonna because those are different frequencies, I'm going to. This is kind of like one of the put our three-dimensional goggles on, and this will pop out at you at the screen. Anyway, because those came from the different sinusoids, I'm going to color code them. Now, let's back up. Let's go to the minus k's. So, for example, when k is minus 1, I'll just write the sums down here. When k is minus 1, we have 2 pi plus, right? Because it's all part of a sum, plus 2 pi times a minus 1 delta of omega plus 2 pi over 5. So this guy is over here, so this is red. 2 pi times 1/2 is pi, times an impulse that's been shifted to the left by 2 pi over 5. So maybe that's right here. Scaled by pi minus 2 pi over 5. So the two red impulses, they differ by 2 pi, and so they're the same frequency in red. That's why there's energy at both of those frequencies. Okay, so the k minus 2 term, no, we don't have that. The minus 3 term, no. Minus 4 term, the minus 4 term is over here, right? So that comes from this sinusoid. That's differing. That came from this sinusoid, so we're going to do it in blue. So that's the k equals minus 4 term. So we would have a minus 4 delta of omega, then plus 4 times 2 pi over 5. So that's plus 8 pi over 5. Okay, so that's blue. So we're going to draw that here. And so that's pi, because 2 pi times 1/2, and then this is an impulse that's been shifted to the left by 8 pi over 5. So that, again, that came from the blue sinusoid, and 2 pi over 5 and minus 8 pi over 5, they differ by 2 pi. And so k goes from minus infinity to infinity, so we have to include all of these things. So this is going to go on forever. So the frequencies that differ by 2 pi and 4 pi and 6 pi, that goes on forever. But this is the final answer. This is the plot of the Fourier transform.